Hi class, welcome to chapter 2.6. Today we're going to talk about transformations of functions. Now this is the important section of chapter 2. So far, pretty much everything should have been some type of review. Again, we do go over things a little bit more in depth in this course at the beginning because it is pre-calculus. All the new stuff really comes a lot later, right? So we really go over algebra again a little bit deeper than normal, and then we talk about trig. The trig is really just a standard review, and then we get into new stuff, right? This, however, is something new. Most students up to this point have not seen the standard transformations of functions. If they have, they've really only seen them applied to their trig functions and probably to a quadratic. So we're going to talk about this for functions in general. This is where your library of functions come in very handy. So your library of functions, along with the transformations that we're going to cover today, are super important. It really makes calculus a lot easier to understand when it comes to the functions that you're dealing with and being able to visualize what's actually happening, right? So we're going to look at quite a few graphs here. We're really just going to talk about how to transform a graph or a function into a new function and how that transforms the graph as well. Okay, so we can transform a graph by shifting it. That's one of the ways. We can reflect it, stretch it, or compress it. So let's start with our vertical translation. A function will be translated vertically. So when we say translation means a shift, basically, right? Moving it from left to right, up or down. So a vertical translation is that movement of a function up or down. So we're not changing its shape, we're just changing its position in space. So to do this, we basically add a constant, which we'll call k, to the end of our function. Okay, so here we have g of x. G of x is our new function, and it is made by taking our original function and applying some sort of shift up or down. Now when k is positive, obviously this increases the output values of my function, so that is a shift upwards. Okay, if k is negative, then I'm subtracting values from my function, so my entire function is now, let's say, 2 less than all of the output values it was before, so it shifts the entire function down by 2 units, right? So here, when k is positive, again, k being a real value, strictly positive, we could also say k is strictly larger than 0. Okay, I'm trying to get you guys used to some of this upper level notation. So if k is positive, notice how the shape of my function here does not change. It is identical. But what happens is everything has been moved up by a certain number of units. Okay, in this case, k is an arbitrary number. So if you look at the distance between this value and this value, it's the same as this value and this value. Even though it looks like this is closer than these are, that's just because of the shape of my graph. It is around 2 units up. Okay, everything here. So from this point straight up, it's still about 2 units. You have a whole unit and then about a half and another half of a unit. Same thing here, right? This is still 2 units up. From here to here, you can see it is exactly 2 units up. Here, this is still 2 units up. Everywhere is a difference of 2 units. Now, what are these units? They could be 100, right? From this point to this point. It could be 5. It could be 1/2. It's not specified, right? But whatever k is, it's 2 of those squares, however much one square is. As you can tell, there's no number line here, but that's what's happened, okay? Same thing if k is negative. K is a negative real value. Everything is shifted down by the same value of k, right? So here to here, it is a vertical translation down of 2 of whatever one of these squares is worth. So since k is applied outside of the function, it's called an outside shift, right? It applies directly to the outputs of our function, right? So it applies directly in the way that we think it would. If I add a value, a positive value, my function gets larger. If I subtract a value, I'm subtracting it from the outputs, my function gets smaller, right? For horizontal translation, it's a little bit different, okay? It's going to translate a function left or right. It also does not change the shape of the graph, it just moves it around, okay? That's what a translation is. So we're going to add a constant h to the input value, right? So we're not actually adding, we're subtracting it, right? So if you notice, this is inside of my function notation. I call this an inside shift, and it actually works in the opposite way that we think. So if I subtract a positive value of h, it actually moves in the positive direction. If I subtract a negative value of h, it actually moves in the negative direction. So you're like, well, yeah, that makes sense, okay? But x minus a negative means that this will look like f of x plus h. So when you see a plus sign in here, you're actually moving in the opposite direction. When you are subtracting something in here, you're actually moving in the positive direction. So when the symbol you see, it doesn't match what you think would happen with your function. So when you see a negative, you're actually moving in the positive direction. When you see a positive, you're actually moving in the negative direction, right? So again, since the h is applied inside of my function, it works in a manner that is opposite of what we would expect, okay? So for instance, when we see x plus 3, you would think it moves us to the right 3 units, but it actually moves us to the left, right? And the reason for that is because it's f of x minus our h is negative, right? So x minus a negative 3 gives us a positive value, right? So we're actually moving in the negative direction. Very, very important to remember that. Next, we'll talk about reflections. If my new function is the negative value of my original function, it's going to flip it across the x-axis. Basically, what's happening is all of the values that were positive are now negative, and all the values that were negative will become positive, right? So it changes my y values. My y's that were positive will be now on the other side and be negative, and vice versa, right? So this works in the way that we think it is. Here, this is an inside shift, okay? It is being applied to the inside of my notation, so it is going to reflect this across the y-axis, right? So here's an example. If this is my function, this would be the negative of f of x. Everything was positive, and now everything is negative, and it's negative in a way that it just changes signs, right? So if this is, let's say, a 2, now it's a negative. I'm sorry, if this was a 1, this is now a negative 1, right? If this was a 2, it's now a negative 2, right? So all the output values change sign, so it flips over the x-axis, right? If I have a change inside of the function, it rotates it around this axis, the y-axis, right? So f of negative x flips it across the up and down vertical y-axis. So now let's talk about vertical, compression, and expansion. We also call this the amplitude. So if my new function is made by multiplying my old function by a constant, that is going to be either a compression or an expansion. It's changing the amplitude of my function. So again, since it's outside of my transformation, it's outside of my notation, it's an outside transformation, meaning it acts directly on the function, right? It acts directly on the outputs. So it's going to behave in a manner that we expect. So if a is large, my function grows. If a is small, my function shrinks or compresses. Okay? So if I am larger than 1, I will grow by a factor larger than 1, right? I'll have expansion. If I'm in between 0 and 1, then I am going to shrink, right? If I'm negative and less than this, then I would shrink and I would flip across the x-axis, for instance, right? So let's say that this is my function, f of x, okay? It's a wave. If I have a large value of a, all of my outputs are multiplied by that value. So if this was a value of 1, let's say it looks like I'm a value of 4, right? Everything is 1, 2, 3, 4 times larger. Then that's going to happen everywhere. Here I'm 0, I'm still 0, right? 0 times 4, output of 0 times 4 is still 0. if this is a value of 1/2, for instance, well, then its output would be 2. Okay, so everything is multiplied, right? Everything is larger, so it just grows the outputs of my function. Now, if I'm smaller, right, it's still a wave, it still has the same zeros, but all of the outputs are less. In this case, my a happened to be 0.25, right, 1/4. So everything is a quarter the size of the original. Okay. So horizontal compression and expansion. So here I have a multiple on the inside of my function. Again, inside transformations work in the opposite manner. For my outside transformation here, if I had a large value a, that made this very large. So since inside transformations work the opposite, if a is very large, that is not going to expand my function horizontally. It will actually compress my function horizontally, right? So again, it acts in a counterintuitive manner, okay? So when lambda is large, my function actually compresses like an accordion, right? When lambda is small, it expands my function horizontally, right? So I like to think of it as a video, right? Like this video. You would expect 2x to stretch my function left to right to be twice as long as the original. But actually what's happening is it's similar to watching a video on 2 times speed, right? If you watch a video on 2 times speed, it doesn't take twice as long to watch. It takes half the time to watch. So it actually compresses my function because everything is happening twice as fast as before, right? So again, it's like watching a movie on double speed. If a movie takes an hour to watch and I watch it on double speed, the time is compressed to half an hour, right? So everything happens in twice the speed. My function is compressed to be smaller. Similarly, 1/2x it means that my original function will be twice as long as the original. It's like watching something on half speed. It takes twice as long to watch it, right? Everything is slowed down, okay? So if this is then this is what it looks like when my lambda is larger than 1, right? So it's a large value, okay? So what it does is it compresses it. Things happen faster, right? When my, when lambda is small, okay, it stretches it out, right? It makes it longer, right? So a large value shrinks it, compresses it. A small value stretches it out. Okay. So the important thing here is that we can combine multiple transformations to a single function all at once. So the functions that you will see from now on, or even in the past, they're really just transformations of functions that we have already. Okay, so if you go back and look at some of the other videos that we've looked at, pretty much everything I've ever given you is just some sort of a transformation of one of those basic functions from our library of functions. Okay, even more so when you get to calculus, if you think about it in that sense, then it makes things a little bit easier to work with. So the order in which we apply transformations matter. Okay, so we apply the transformations in the same way that we would apply the order of operations to x, right? So whatever x would look like in that expression of the function, that's the order that we apply the transformations of our function, right? So example, if h of x is 1/2 square root 2 times x plus 3 minus 4, this is really just a transformation of the graph f of x equals square root of x, right? I'm just applying several things to it, right? The first thing that I do, right, is again the same thing that I would do order of operations wise to x. The first thing I do to x, if I had to evaluate this, if I said x was 3 and I said figure out the value of this function at the value of 3, the first thing you would do is add 3 to it. So the first thing I do to graph this function is I take the square root of x function and I translate it left 3 units, right? This is inside of the function, right? So to the left 3 units. So remember, inside of the function square root of x, this looks like x minus a minus 3. So that's to the left 3 units. Even though it says plus, again, it's inside of my function, and that function is the square root function. So the way this applies is x minus a minus 3. I move it left 3 units of this graph, right? So this graph, I would take it, move it to the left 3 units. Next, I would compress it horizontally by a factor of 2. This is, again, 2 is inside of the square root sign. So that's a horizontal compression of 2. Okay. I then would compress vertically by 1/2. This is less than 1, so it makes everything, all output values, half as much as it was before. And then to that, I will translate all of this down 4 units, right? So if I took g of x equals 1/2 2x plus 3 minus 4, notice the difference here, okay? So it's clear by looking at it that they are 2 different functions, but the way that I would graph this is possibly what you would think I would do here, right? Which is the first thing that is being done to this x is to compress my graph by 2, okay? Then to that, I translate it left 3 units, then I compress it vertically, and then I translate it forward. If I plugged in x equals 3 here and x equals 3 here, I would get out 2 different outputs because these 2 functions are not the same. So if I take this function and I translate it this way according to what's happening here, I will get a different result than if I take this function and translate it this way, right? And again, the only difference is that 1 and 2 are switched, right? 3 is still compressed vertically by half. The 4 is still translated down 4 units. It's just that here I need to translate left 3 units first. Here I translate left 3 units second. So if I switch my order of operations, right, I'm going to get a different graph out. I'm going to get different sets of outputs out. So the order that I apply these is important. Okay. So again, notice that the difference is slight, but the difference in the result is different graphs, right? So if we distributed the 2 here, I would have 2x plus 6. Okay, that would be the same function. So that means that if I had this equation and I translated it this way by compressing horizontally by a factor of 2 and then moving left 6 units instead of 3, then I would get the same exact function as this first one, as this h of k that I have. Okay, so here you go. This is the square root of f of x. So I would get h of x if I applied all those transformations, right? So let's go back here. Translating left 3 units, then compressing horizontally, and then by vertically, and then down 4 units, right? So if I did all of those, step by step by step by step, I would get h of x, okay? If I did what I outlined in g of x, this is where I end up, and as you can see, they are 2 different results, okay? So let's do another example. So let's apply the transformation 3 times f of x minus 2 plus 1 to the table of values for f of x, right? Right, so I'll give you a table of values in just a second, but look what we have here. We don't know the actual function. We only know the transformations of it. So if we go back to this last example, okay, if I wanted to, I could write this in terms of function notation as 1/2 f of 2 times x plus 3 in parentheses and then minus 4, right? So instead of a square root, I would just fill that with f of x, right? So again, I would write 1/2 f of 2 parentheses x plus 3 in parentheses and the parentheses for the function notation minus 4, right? So all I'm doing is taking the square root of x and really just applying those shifts into the function notation, right? So that's if I didn't know what my function f of x was. So here it's the same thing, right? I don't know what f of x is, but I do have a table of values for x, right? I'm only given certain inputs and then my functions. So if I want to apply these transformations, right, I can try to do it all at once, but that's probably not the easiest way to do this. An easier way would be to do this one at a time, and again, doing it in order of what would be happening to x if I knew what f actually was. Okay, doesn't matter if f is a linear function, doesn't matter if f is square root, doesn't matter if f is a piecewise function. It really doesn't matter what f is, because the order that things happen to x is always the same. So as you can see here, it doubles, add 1, minus 2, minus 3. Who knows what this function actually is? It doesn't resemble anything that we actually use, right? It doesn't look like an x squared function. It's possible that this is a piecewise function. I have no idea what the actual formula form of f looks like. But I can apply these transformations. So the first thing that happens to x is that I subtract 2, okay? Which results in a horizontal translation to the right of 2, right? Then I multiply things by 3, and then I would add things plus 1 to the end of that. So I'm going to apply these transformations one at a time. So the first thing I'm going to do is I'm going to take my list of values. If I need to move everything to the right 2 units, that means that instead of 3 being an output at -2, 3 should be an output 2 units later at 0. 6 should be an output 2 units later at 1. 7 should be an output 2 units later at 2. 5 should be an output 2 units later at 3. 2 should be an output at 4, and -1 should be an output at 5. So then the question is, well, what are the outputs for -2 and -1? I don't know. I don't have enough information to answer that. Okay, but so I just put x's there. I could put question marks if I want. It's just something to specify that I don't know this information, and everything moves to the right. Okay, because that's what this transformation does. It moves things to the right 2 units. So everything moved 2 units to the right. Okay, it's actually very simple. Now the next thing that would happen, right? So let's say that this was 3 of x minus 2 squared plus 1, right? Let's say we ignore this f and we made up a function. Let's say it was a square root or a cube or something else. This would be the first thing that happened to it. The next thing would be times 3. So for my next thing, okay, transformation, I'm going to take all the values I had previously in the exact same position, right? Because I've already applied the x minus 2. This is an outside transformation. It's outside of my function notation. It happens directly to the output values, right? The x minus 2 did nothing to the input values, but it did to the output values, but it did move them according to the inputs, right? So this applies directly to the outputs. So all the outputs I have here multiply times 3. Okay, so that's still unknown. Still unknown. This becomes 9. This becomes 18, 21, and 15. Okay. The next thing that I do is I'm going to add 1 to all of those, and that will complete my transformation, right? So I'm going to have 10, 19, 22, and 16. This is the final set of outputs. So this is my original inputs, and I'm applying this transformation here. This is the new set of values I have out. So these values get translated to this. This 3 turns into a -10. This 6 turns into 19. This 7 turns into 22. This 5 turns into 16, right? So that's how the outputs change, and they also change where they're located input-wise. That's how that works. Okay, so now we want to graph the transformation -2 times my function with the applied inside shifts, right? So there's a couple of things that are going on here. -3 for the given graph of f of x. So here we can think of things in a couple of ways, right? That is, we can first apply this -1/2, this expansion horizontally, and then shift it horizontally to the right by 2, or we can factor something out so that it looks more like what we had here, right? So that we apply the horizontal shift translation and then the horizontal compression. It's really up to you. A little bit of extra work. It might make it easier to first shift things and then expand it, but again, it's really up to you. I went a little too far there. Okay, so let's say that this is my function f. Okay, So if I want to apply these transformations, I'm going to apply them, again, I apply them one at a time, right? So, okay, this is my f. Coming over here, I kept this here because these are the transformations we're going to apply. So again, this is my f. So first thing I did was I applied the 1/2, right? I made everything twice as long. This happens at 3. Now it happens at 6, right? This down swipe happened at 2. Now it happens at 4, right? It's twice as long. This happened at 1. Okay. Now it ends at -2. This ended at -3. Now it ends at -6. Okay. So remember, it's an inside shift, so it does the exact opposite, right? It does not make things compressed to half of what they were. It does the opposite, right? So you're really looking at the reciprocal of this. It's making everything happen instead of at 1/2 at double times, right? So everything's happening at half of the speed, so it takes longer to occur, okay? Next, we have to apply this negative that's on the inside, okay? So remember, an inside transformation for a negative value, that does not change my outputs, it changes the inputs. So that rotates it, it reflects it across the y-axis. So this point that's here at 4 will move to -4. Okay? This point that's here at at 6, -1 will happen at -6, -1. Okay? Everything's going to rotate across this axis, right? This that's at -6, 1 will come over here. So the whole thing will flip around. Okay, this moves over here, this moved over there, etc. So now we're looking at this thing. Okay, so that's the difference. Right, so that's clear what's happening here. So that's the flip across the y-axis. The next thing is I need to do a horizontal translation of 2 units to the right. Again, it looks like a -2. You would think we move it this way, but remember, it's minus a positive value, so we're moving it this way. Okay, so first transformation, flip it around the y-axis, and then translate it to units. So this one will be at -2. This end right here will be at the 8. Okay, so I was here, flipped it around the y-axis, and then I moved it over 2 units. The next thing that I do is I apply this -2. So I can do that one at a time by first doubling everything and then flipping it across the axis, or I can flip it across the axis and then double it, or I can do both at the same time, which is what I did. So this was at 3, it moves to 6, flips because it's negative across the y-axis, and now it's a -6. Okay. Same thing with this value, it was a -2, it grows to -4, and then it flips to here. So expand by a factor of 2, translate, rotate across the y-axis, move it 2 units, multiply by -2, so it flips across the x-axis and it grows. The next thing I do is I take this final result here and I move it all down 3 units. So this point will move down to -9. The value, this straight line right here, will move down to a -5. This endpoint that's at -4, -2 will be at -4, -1. And that's my end result. Okay? And that's how we apply transformations to a graph. Plot your graph several times, one transformation at a time, in the order that's appropriate until you get to your answer. And that's how we apply transformations. Graphically, algebraically, and through a table of values.